Hello, guys. Hello, and welcome to this KSS session today. Very nice to see you all here. I can see everybody looking very active, and it's so nice to be here. So let's go directly into the business of the day. So we're looking at the inside transformer networks, a deep dive into attention mechanisms, architecture design, and the models powering modern AI. And I'm Louis Nwadike, an AI engineer and founder of LaserVolt. So let me walk you through what we have for today. So just to give you context, the modern day AI architecture was basically powered by the transformer model. Before then, we had mostly sequential models that prompted for very high processing power because they were very sequential. So they took more time to train and also entailed high processing infrastructure processing capabilities. But with the transformer networks, we have less sequential and more parallel models. And that was what gave the edge to the modern AI that we have today. So that models can be able to be trained faster and with lower infrastructure resource or electricity consumption. And this is done by having parallel processing. So the transformer network, the transformer architecture was what gave rise to that explosion of better paradigm in the AI shift. And that's why we have open source models today, and we also have widely used models today, all thanks to the transformer model. So that means that it's worth studying the model. And we're going to be looking at that today, starting from an introduction to the transformer models. So transformers are neural network architecture designed for sequence modeling and transduction tasks, such as language translation, text generation, and speech processing. So we have linear data, we also have spatial data. So transformers were originally designed for linear data, sequential data, like text, speech processing, or autoregressive text generation. And that entailed that it was reading on linear data, transforming that to tokens, and using a syntax of architecture and learning about the context of the data it was working on. So the key characteristics, based entirely on attention mechanisms, it eliminates the recurrence, the RNNs and the convolutions. So before that we had recurrent neural networks, the RNNs, which by concept functions very similarly to the transformer model, except that it's more sequential, while the transformer is parallel. So based on the concept of architecture, what they both do is almost the same. So they're both having data that have been transposed to embeddings, and those embeddings are simply vectors, and they are translated to vectors because vectors are able to capture more data, more context, or more meaning of the data, and then they are basically juxtaposed. So you basically concatenate and juxtapose these embeddings to derive the context or to learn context out of it. And we do that using mathematical formulas, and you're able to get proper context of that data. So that's the whole high-level overview. The transformers and the RNN by basic concept of embeddings, juxtaposing embeddings, and also filtering those concatenated embeddings. They function based on the same linear principle. However, where the RNNs were done sequentially, the transformers are done more parallel. So that's the edge it has over the older models that we had there. So it's highly parallelizable on GPUs. It forms the foundation of the large language models. Today, nearly all major AI models use transformer architecture. Examples include the BERT, the GPT, everyone uses GPE. I don't know who hasn't used GPE, given that it's one of the very first open source models out there that came out to public consumption. Then we also have the vision transformers. The historical background of sequence models. So before then, before transformers, we had sequence modeling, which relied on the recurrent neural networks, the RNNs, as we previously mentioned. We also have the process tokens sequentially. Now the problem there, as I mentioned previously, is that it now becomes very slow to train, long range dependency issues. So when you're training for a very long context window, you're training large amounts of data. So we have deep and large neural networks. It means that we're going to lose data due to the mathematical principle that powers the learning cycle. That leads to vanishing gradients. Because by concept, the way these models learn is by a very fundamental principle which we call backpropagation. It basically propagates gradients based on loss. So I don't want to go into details yet, but the architecture is that we have neurons, we have different data sets translated as neurons, and they are passed into a black box or a neural network. And these are all like interconnected nodes that get to hold data. We call them weights, and they are scaled by a bias, and they are then forwarded in a forward network down to what we're supposed to have as a target, and then we compute the loss, and then we backpropagate the gradient of every neuron as relative to the loss function. So that's we call that partial derivative. So that's a much broader concept, but this is the fundamental of how these work. And in doing that, given the previous networks we had, like the RNNs, it entailed that with very long context and long data, large data sets and deeper neural networks, that gradient over time, based on the forward and backward propagations, the gradient just becomes very small, that when used for computation, it leads to null values. So that's what we call vanishing gradients. So before the transformers, we had these issues so much, but using the more equal architectures that we now concise into a transformer model, we've been able to solve those issues. And we've been able to see very great progress, both on the sequential data sets or spatial data sets where transformer models have been used. We've seen very great outputs in them. So we have the LSTMs and the GRUs. We have improved RNNs, but still sequential. Then we had the attention mechanism, which came out 2014, which was introduced to help models focus on important tokens, but they were still used inside RNN architectures. So we had an attention mechanism that came out, but they were still used in the RNNs. So this is just giving us an evolution down to, from the RNNs down to when we were able to get the transformer architecture, which was the major breakthrough. And it's based on a concept that attention is all you need. So I'm going to go more deep into the concept of that. Attention is all you need. I'm going to liken that to what we're talking about, the transition in the history of AI models and what we've evolved into, and the future possibilities of the new models we can also evolve into the future. So as of 2017, we had Google researchers that produced the Ashish Vaswani and his team at Google produced the Attention is All You Need paper that delved into the transformer model. Transformers were introduced in the landmark paper, Attention is All You Need. The key innovations include self-attention replaces recurrence, fully parallelizable architecture, improved translation accuracy, benchmark achievements, blue score of 428.4 on WMT 2014 English German, and also a blue score of 41.8 on English French translation. So it was the result that it surpassed existing models while being trained faster, all thanks to the parallelism that was introduced by the transformer architecture. So we now have models that are way faster to train and also produce better results compared to the previous ones. Now, what's the high-level transformer architecture? A transformer basically consists of two major stacks: the encoder stack that processes input sequence and the decoder stack that generates output sequence. The structure is the input goes into the encoder stack, the context is represented, passed into the decoder stack, and then we have the output tokens. Each stack contains n identical layers, so we have multiple layers of each stack, going from the input to the encoder, processed out back again to the decoder, and then the output. The original transformer model consists of both encoder and decoder models. So I know you might be hearing the encoder decoder and might be sounding a little bit strange, but I'm going to dive deep into that progressively. So just stay tuned with me. I hope so far we're all following what's going on and we're all following the sequence of context we're moving from the RNNs down to the transformers. So the original paper used 6 layers. So we denote that as N, and each layer consists of multi-held attention, feed-forward network, and residual connections, and layer normalizations. Now, this is the picture. This is the original paper. This is what we have from the transformer architecture. It basically gives you the basic concept of all you have in the transformer model. So everything you see here can be interpreted, and it's basically going from, you have the positional encodings going down through embeddings. We have multi-head attention. We add normalizations, and we have a feed-forward network that passes also into another layer of normalization. So it's like you're going feed-forward, you processing this sequence of tokens, and then you also pass that embedded, that encoder processed output as an input again to the decoder, and then you have masked multi-head attention again, and then you pass that through again through normalization, addition, you add and normalize, and then you have a softmax after a linear regression, and then a softmax operation that now predicts the probabilities. So the activation function at the end, that's what does the basic probability calculation, and that's basically how the models work, because they all work based on probability, and it's the output that we get to choose the most probabilistic event that is to occur that fits into the sequence of already generated tokens. So that sequence, using that sequence as context, we're able to predict the next sequence that's supposed to occur. So I'm going to dive deep into this in the future, but I'm giving more examples so that we have better context of what's going on. The transformer encoder architecture. Now, this is a very good high-level overview. Each encoder layer contains encoder layer. It contains multiple layers. Multi-held self-attention. We have add layer normalization. We have feed-forward networks. Then we have normalization again. So, and that goes through an input embedding, positional encoding, multi-head self-attention, add and layer norm, then feed-forward network again, layer normalization again, then encoder output. So this self-attention ensures that every token is able to attend to every other token. So what does this mean? For example, we say the cat is on the mat. When the AI models process that sentence, the cat is on the mat, it doesn't know English language. It doesn't know what you're talking about. It doesn't know any language you're talking about. It only knows its data and it knows its tokens. So when you have something like that, what it basically does is that it tokenizes that sentence. It splits it into multiple tokens based on several patterns, be it character level, sub-word level, or word level. It tokenizes each of those splits that it's done, and it's able to use that as the basis of its operations. So when you have the cat is on the mat, it basically learns by the large data it works on, and it's able to know that whenever I see the cat is, the next should be what? On. And after that, the next should be what? The. And after that, the next should be mat. So that's the high-level overview of how it gets to learn using all these tokens, and then it's able to predict what's supposed to happen next. And then given that it's been trained on a very huge number of data, large amounts of data, and also deep neural networks, that's the whole framework of what's going on, the deep neural networks. It's able to capture intricate details and context about the data it's being trained on. Now let's talk about the decoder aspect of the transformer. The decoder is similar to the encoder, but has 3 attention layers. 1, the masked self-attention, 2, the encoder decoder attention, and then the feed-forward network. Masked attention ensures that the tokens only sees, so token T only sees token less than T. So it only sees the tokens before it. For the encoder, as I previously mentioned, for the encoder model architecture, It basically processes the entire data stream such that every token sees the token before and after it. That's the encoder pattern. But the decoder only, it gets to mask the computation such that every token only sees the tokens before it when it's deriving its computations. And that's the power of a decoder model. So it's able to do that auto-regressive token generation just based on the tokens before it. And these two architectures were compiled to form the transformer. However, as we're going to see in the future, models like GPT and ChatGPT use decoder only because it fits a certain problem set. Even though we're looking at AGI in the future that combines multiple model types, but that's the basic of how the GPT model works. Generative pre-trained transformer. They're basically decoder only, and that just reads from the tokens before and is able to auto-regressively generate the next tokens based on its previous tokens. So we're looking at embeddings and positional encoding. Since transformers process tokens in parallel, they need positional information. So you're processing information in parallel. So you should be able to know these tokens that represent they are actually vectors. They are embeddings, and then these embeddings are basically vectors. And these vectors are simply stream or collection of data, collection of numbers that represent a real world entity. So they have real meaningful value. And that's the whole concept, because you're trying to capture the meaning of data. You're trying to capture the context of data. And that's why they are translated into embeddings. And these embeddings are able to capture the meaning, intricate meaning of data in a given context. So since the transformers process data in parallel, they need to know what's the position of the information. So the cat is on the mat. What is the position of cat in the sentence? In that sentence, the cat is in the second position in the sentence. But when tokenized, I want to be able to map the token generated based on whatever token paradigm I choose. I want to be able to map that to the actual sentence I'm working on, which is my data. So that's where positional information comes into play. So the input tokens, as we mentioned previously, are converted into vectors. This is a set of real numbers that's given by the sequence length times the model dimensions based on what embedding dimension we choose. Typical model size, the D model 512 or 768. Now we even have longer model sizes, longer embedding sizes that get to capture more data, more context about the data. So this is just like the mathematical formula involved in giving that positional encoding. Now, these functions allow models to encode relative positions, as I previously mentioned. Now, this is a very interesting one. I don't know if anybody's heard about the QKV representation. Anybody? A very interesting one. And this is one of the backbones of the transformer architecture. This is what the transformer architecture prides on. So basically, what it does is and that's the whole concept of the self-attention mechanism, is that every token in itself is translated into 3 different embeddings. So the query, the key, the values. And who can remember what we spoke about embeddings? So embeddings are basically vector representations of data, of tokens. And vectors, as we previously also mentioned, is that it's a set of data, not just a set of data, but set of data that hold meaning. So for example, let's say 2-dimensional vector, when you say X and Y, X can represent what? On a geographical Cartesian plane, 2D plane, X can represent the X axis, Y can represent the Y axis. This is not just graph, this is information. This is data. You can map that to real world entity. And that's the whole concept. It's not magic. You're mapping real world patterns, real world data, real world entity into mathematical formula. And that's how you're able to derive meaning out of it and make sense out of it. So coming back to the QKV, every token is represented as QKV, and that QKV is now used in computation. So it's used for projections that allow the model to search, which is the query. What am I looking for? The index. key, and then they retrieve information. What value do I have, or what value am I able to get? So these tokens are able to learn about themselves. So you have multiple tokens, you juxtapose them, you perform mathematical operations on them, and in doing that, they're able to learn about their positioning and about their context. And that's the whole concept about transformer architecture. They're learning about the context. Each of them is being concatenated, it's being filtered on, is being juxtaposed, and it's able to learn about its context in a given pattern. And that's the whole power, that's the whole beauty of the QKV architecture. Every token is represented in 3 different embeddings, and these embeddings are juxtaposed or work together. And that's also what gave us the concept of self-attention, because you yourself, a token in itself, is able to operate on itself, so that it's also able to learn its own context in a given data set. The core attention function, we have the QKV, and then was previously mentioned, the softmax is the activation function at the end. Previously, like in the black box, in the neural network side, we have multiple kinds of activation functions, including the relay, the softmax, the tanh, and others. But the softmax in the transformer is usually used for the output. So when you've gone through all that black box, you've gone through all the neural networks, you've gone through multiple layers you want to work with, multiple dimensions, you've done all the computations, all the normalizations and all that, all the filtering. And then you want to go out to our output that maps the input to the target. And that's where probability comes in. The softmax is what the activation function that coordinates this, and it gives us the probability of the multiple outputs based on our inputs. So it's very interesting. It's a very interesting concept. And this is how the model is able to learn about real world data and have predictions that actually match the pattern that is being able to learn of. So this generation is context aware. It's a context aware representation. Now, very interesting, the multi-head attention. Instead of one attention function, transformers use multiple heads. For example, for head I, we have head I attention into head I attention into QW and all that. So we have multiple heads. Instead of a singular head, we have multiple heads that are being what? Concatenated. And what now is this is just the high level of it. Now, what it simply, the purpose of this is for it to be able to do what? To learn multiple relationships. That's the whole purpose. Like, if you look at the actual code behind the whole transformer architecture, it's technical, but I wouldn't say it's complex, because by concept, the meaning of it is very explicit. You'll be able to like get the meaning of what it's doing. And if you follow the metrics calculations going on and all the scaled products that are going on, you'll be able to derive meaning out of it. And that is very interesting. And that's why it can be applied to any real world entity, and you'll be able to get real value out of it. You'll be able to get real result, because you're simply mapping what's already an existing pattern, and you're able to derive the meaning using mathematical principles, and you're now able to use that meaning to form future predictions. Now, this is a sample code of the transformer architecture. So this is an encoder layer where we have, this is just like the feed-forward network. So we'll first initialize, we normalize based on layers, based on the number of dimensions we have. And then very importantly, the dropouts, because that's what helps us to avoid the vanishing gradient problem. It also helps us to avoid overfitting or underfitting. Now, the encoder only versus decoder only models, and then versus the encoder to decoder. So we have encoder only models, like the BERT models. We have the decoder only models, like the GPT models. And then we have the encoder and the decoder models, like the T5 and the original transformer. So all what we've been talking about so far have been about the transformer model, the original transformer model that was able to capture both the encoder and the decoder. But progressively, researchers have been able to see that we can actually implement this in a certain way, that we can have a decoder do certain kinds of functionality that it's best at, given that it's auto-regressive and it only sees context before it. It only sees the tokens before it. Because why? Because we're masking the tokens after it during the computation, which we're not going into the very low level details about it. But During that, the training process, we're able to mask, and that's the filtering process. We're able to mask data, we're able to mask tokens before it, so that when we're doing the QKV computation, it's only able to work with the data before it. And that's what the decoder model is very good at, and that's the principle it uses. And that's what GPT also uses, and it's able to produce very, very great results, given that it only sees tokens before it. The encoder model, however, sees the entire context, and that can also it also has its own use cases, just the way we have BERT models that are very good for understanding. For example, if you're doing speech synthesis, for example, you want to know the whole context of the speech, and if you want to do like summarization, you'll be able to summarize that based on the entire context. It's not now very important to know both the decoder only models, the encoder only models, and the encoder decoder models can be able to learn all this, the different scenarios, the different use cases. It can be able to do it. Just that some models are better suited for some certain tasks because of their training architecture. And in the end, all they do is what? All they do is what? They map input to output sequences. Now, let's look at the examples of GPT transformer architecture. Modern LLMs like the GPT-4 use decoder-only transformers. The key characteristics include auto-regressive text generation, casual max attention, extremely large parameter counts. Example scales. Training involves massive data sets and distributed GPU. So we have models like the GPT-2, which had 1.5 billion parameters. When we say parameters, we're talking about the weights and the biases. So weights are applied on every token, on every neuron, while the bias is applied on a layer. So based on how you represent the vector, it's applied as a constant value on a layer. However, it's also a learned value. By that, I mean that the value changes as the model learns. As you do the feed-forward network and the back propagation, as the model learns, the values also change. However, it is constant for every layer. So one value is passed to project the transformed linear combination that have been done by the weights on every neuron in a layer, and then you project that using the bias. The bias comes into play in that we have a data set and we have a target we want it to meet. If you represent that in a 2D geometrical landscape, we want to be able to go from point A to point B, whereas maybe during our linear transformation using the weights, linear combination, which is the multiplication using the weights, we're not able to really get to the position of our Y on our X. So what we simply do is that we project that using the B, that's the bias. So in the same vector direction, we want to project, we want to scale that vector to be able to hit our target. And that's the whole beauty. And that's the whole concept behind what transformers do. You basically linear transforming data. You basically using linear combinations and partial derivatives to transform data from one direction to a different direction that meets a target, and then use a bias to project the direction, the vector to hit the actual target in a specific direction. So that's the whole concept. That's the whole mathematical and graphical concept of what these models try to achieve and how they're able to map input to output. Now let's look at the performance metrics and benchmarks. The common evaluation matrices, the BLE, machine translation accuracy, the perplexity, language modeling performance, we have the exact match, F1, question answering task, we have example benchmarks improvements that involve the transformer significantly improve the translation quality. So we have multiple scientific and technical benchmarks that we use on these models. So when you have a model, you have to benchmark that. Does anybody understand what I mean by benchmarking? Anybody? Perfect. I can see some very optimistic people around. So benchmarking just simply means that we have a standard, we have a prerequisite of output the model is supposed to be able to achieve. a prerequisite of accuracy the model is supposed to be able to achieve. That's the benchmark. So we pass it into a given context or data set and see how it's able to produce results based on certain benchmarks. So we're looking at the infrastructure costs, we're looking at the speed, we're looking at the accuracy. So several standards are put in place to ensure that these protocols are met and that the model is able to achieve very good performance. So when you're comparing that on our BLE, we have RNN, like sec to sec, sequence to sequence. We have approximately 24 score. What the transformer model was able to give us 28.4 score. Given that also, it also involved what? It involved a less running time than what we had with the sec to sec RNNs. Because what? RNNs were basically sequential in processing, while transformers were what? Parallel in processing. And that's the whole edge. That's where it gains its edge over the recurrent neural networks. Limitations and future research. Despite success, transformers also face challenges. Obviously, it's still in a very progressive stage. It still has very good improvements that we're able to give into it, and it still have very long way, given that the whole AI architecture is still improving. We recently got the GPE 5.4, and it's been a very good improvement. We've also been able to see applications of transformer models into CNNs. So instead of just having the normal spatial data processing CNNs, we've been able to see cases where transformers are able to also integrate into those other kinds of models. And we're able to use that same concept that was derived from the QKV transformer sequence architecture down to also spatial or non-sequential data, and also achieving very good results. So we also have some of the limitations we have with the transformer architecture is that it has quadratic complexity, the self-attention cost. With sequence length, you have the O of n squared, it just goes really high. It basically needs very good memory requirement. You need very good memory. You need GPUs, you need TPUs. We also have LPUs. We just basically need very good, very high infrastructure processing units that are able to give you good results. Now, just to touch on that, one of the good parts of the transformer architecture is that it's able to give us parallel processing and GPU processing. Sorry. So we're able to process on the GPU itself.